It's good. Good. We're broadcasting. There we go. So we're looking at the scalar equation of the plane, and we've already looked at the in R2, or in 2 dimensions. Scalar equation of the plane takes on this form: 2x minus 3y plus z minus 4 equals 0. Okay, and so it's got coefficients in front of all of those numbers, and it's all in one line, so it looks kind of nice. If you recall, the scalar equation of the line had this convenient form that told you what the normal to the line was. So, you know, if you were given the normal to the line, you could figure out what the equation of the line was. It was pretty easy. So first thing we're going to do, we're going to figure out if this general equation of scalar equation of the plane is related to the normal vector, okay? And we're actually going to do it by taking the dot product of the normal vector to a plane, and that normal vector has a, b, and c as its coordinates, expressed as a position vector. And then we're going to dot product that with a general vector that lies on the plane from a specific point. We're not giving it numbers, though. We're giving it the coordinates x naught, y naught, z naught. So the tail's there, and the tip is going to be at x, y, and z. And x, y, and z we're just leaving as x, y, and z so that we can come up with an actual equation. Okay, now the good news is when we take the dot product of anything on the plane, any vector that lies on the plane with the normal vector, it's going to be equal to 0. Okay, so that means that a, b, c dot, and I'm going to do tip minus tail, x minus x naught, y minus y naught, z minus z naught. That dot product is going to be equal to 0 because those are going to be perpendicular. Okay, dot product, that's easy. A times x minus x naught. That's a times x minus a times x naught. Plus b times y minus b times y naught. Plus c times z minus c times z naught. That whole mess needs to be equal to 0. Now, it's not obvious because we're using variables for the point that actually lies on the plane, or symbols rather, but x naught, y naught, and z naught actually represent real numbers. So I'm going to shuffle them over there. I'm going to segregate them like the different entities that they are. Okay, so ax plus by plus cz, I've collected all those together, minus, and these are all subtracted, so I'm just going to put a big minus sign there. Ax naught plus by naught plus cz naught is equal to 0. Okay, so look at this. This is already turning into that scalar form that we liked so much when we were using the equation of the line. Now we have this thing that is actually all just numbers. And so this whole thing is really a constant. And we are just going to conveniently ignore it, but for any value, any selection of x naught, y naught, and z naught, this thing is always equal to the exact same value. It's a constant d, so it's not exactly a proof. This is not the proof that you are looking for. You can move along. We're just going to call that d, or we're just going to be adding d because it's a constant, plus d is equal to 0. And so the scalar form of the line, a, b, and c are actually the normal vector, okay, or a normal vector. And then there's a d in here. And the d we're going to have to figure out for specific circumstances. Okay, so let's switch this up. I'm going to give you a normal vector and a point, or maybe I'm going to give me a normal vector and a point. And we're going to find the equation of the plane that passes through that point and has a normal vector. So find the equation of the plane. Uh-oh, I'm mixing fonts here. So let's pick a normal vector. Any normal vector. We can do this. This is going to be easy. Maddie, what's your favorite normal vector? You don't have one. You love them all like children. Nice. I am kind of partial to 1, -2, and 3. And this plane with that normal vector passes through the point. What point do you want, Aiden? Pick a point, any point. Not with big numbers, though, because it's just mean. 2 and 3, and then we're going to need a z value. 2, 3, 1. I like the numbers 2 and 3 and 1. They're easy to work with. Okay. 2 ways I could do this. First way is hard. The second way is not as hard. I could go through this whole thing I just did where I do the dot product of the normal and some abstract vector that's sitting out on the plane. So I could do the dot product of 1, -2, and 3 with x minus 2 and y minus 3 and z minus 1. Set that equal to 0, expand everything, collect like terms, simplify it, make 2 or 3 mistakes along the way. Right there where I said make 2 or 3 mistakes, I decided that this is just too hard, okay? There's a simpler way to do this. Since this is the normal vector, and I know that that's my ABC in the plane, I'm just going to start to set it up this way. So this is 1x. You don't have to write that x. Minus 2y plus 3z. Oh, darn, that d keeps showing up. Okay. I know that it pretty much looks like that, but here's the problem. I don't know what my d is. D is for darned. But I can see that someone out there on the internet has it figured out. How am I going to figure out my d? Maddie?
Can you sub in the points and then just set it equal to 0 still?
Yeah, so I'm just going to substitute the coordinates of that single point, and they're going to satisfy the equation of the plane, and that's going to get me the value of d. So 1 times 2 minus 2 times 3. Aiden, you really know how to pick your points. Plus d equals 0. There we go. 2 minus 6 is -5, plus 3 is -2. So d is 2. Look at this. D is 2. So if you've got a whiteboard, you can actually erase this d now and put a 2 there. That's the equation of the plane that's normal to that vector and that passes through that point 2, 3, and 1. I could have done it this way, so that's an option. It's just a little bit harder. I don't like hardness. Okay. Actually, I'm not worried about hardness. I just don't like subtracting negatives. There's something about it. Doesn't agree with me. Okay. Here's something else that we're going to do today. So we're going to find the formula for the distance between a point and a plane. So if you remember, whenever we're talking about distance in the vectors and algebra world, it means perpendicular distance, right? So we're always talking about that closest point of approach between any point and a plane, okay? So here we are. We have, here's our normal vector to the plane, A, B, and C. Here's our point on the plane, same point as before, oddly enough, x naught, y naught, and z naught. And randomly out here somewhere is a second point. So I'm going to call this one P, And I'm going to call this one out here Q. And we're going to give it the actual coordinates, x1, y1, and z1. So we're going to use this whole thing to develop a general formula to find the distance from a point to the plane. Okay, so the point has coordinates x1, y1, and z1. Okay. Now, if I just join P and Q, so P is just some random point on the plane. It was walking by and I said, hey, do you want to help me find the distance from this plane to a point? And it said, sure. So we've enlisted it. And the actual point out here is x1, y1, z1. We have the tools, though. We know how to find the distance between two things. We did it in 2 space. Now we're going to do it in 3 space. We're actually going to project PQ onto the normal vector. So we're going to do that orthogonal projection thing. And we're going to use our formula for that. So we're going to project PQ onto our normal vector. Believe it or not, this is going to give us a nice formula when we're all done. Okay. So the projection of PQ onto N, that was equal to the absolute value of PQ dotted with the normal. And then it was all over the magnitude of the normal vector. And I know you guys remember all that, so we're all right. This is going to result in a formula. It's not going to be pretty to start with, but you'll see. It's going to pretty up a little, pretty nicely. Pretty up pretty nicely. Okay, so PQ, I'm going to do tip minus tail. So this is x1 minus x naught. So there's my x component of PQ, and then y naught 1 minus y naught, and then z1 minus z naught. So there we go. There's my vector from the plane out to that point, and I'm going to project it onto my normal vector. So I'm doing my dot product in the top. And then this thing is all going to be over the magnitude of the normal vector. And you probably remember this is just doing 3D Pythagorean theorem. I don't know if they had 3D back in Pythagoras' day. Okay. This is looking kind of a lot like what we did before, where we were doing the dot product and we had A, B's, and C's. Here we go. So I'm going back up here. AX1 minus AX naught plus BY1 minus BY naught plus CZ1 minus, oops, yeah, that's a 1, minus CZ naught. Okay. We're all good. There's the top. And here's the bottom. Good old Pythagorean theorem. There we are. Okay. Keep in mind, unlike the last time we did this, all the x's and all the y's theoretically are numbers. Okay. Now what I want to do, x naught, y naught, and z naught, they all actually lie on the plane. And so they're actually going to fulfill that equation of the plane. So I'm going to gather them together. And they're all being subtracted. There we go. That's all over the magnitude of the normal vector. Now, AX naught plus BY naught plus CZ naught plus D. Those points all lie on the plane. They're going to satisfy the equation of the plane. And so these are all actually equal to negative D. Okay? So this expression right here, I can actually substitute a negative D into it. I'm exhausted from all this writing. So this actually just becomes plus D on top. And I can shorten it up. That's an absolute value bracket, so I make it extra big. There we go. So believe it or not, doesn't look like it at this point. This is our formula for the distance from the plane with the normal ABC to a point way out hanging in space. The coordinates of the point are x1, y1, and z1. How terrible was that? Okay. Going to do an example, but we're going to wrap in up like a couple of little, we're going to put a twist in our example, which is just a nice way of thinking about or looking at another kind of problem solving. Okay. Aiden is rubbing his eyes and wiping his face and stuff like that. This is getting serious. Maddie, you're also rubbing your face? Okay. Home Alone 2? No. Okay. So let's find the distance from the plane Now I'm going to give it the equation of a plane, and I'm going to give it in vector form, and we're going to see how we can go from vector form to scalar form. So this is like two things all wrapped up into one. Okay, so here's my plane. So give me a position vector. Maddie, I know you can do this. Position vector, nice and simple.
0, 0, 0.
Oh, that is too easy, maybe. 0, 0, 0. Let me see. I have to just. Will that be?
No, that'll be messy. Would it? I thought that would make it kind of terrible.
No, I don't think so. That gives us a D
Here.
value of 0. It's actually an interesting. It's an interesting problem to think about, because all we need to do actually is find the. Yeah, let's go with 0, 0, 0. Let's see where it takes us. Okay, good. And I need two direction vectors. Aiden, give me a direction vector, and it better not be 0, 0, 0, because that definitely won't work. 1, 2, and 3. Okay, there we go. 1, 2, 3. Okay, another position vector.
4, 5, 6.
4, 5, 6. Okay, all right. I don't know where you guys are coming up with these numbers. All right. Okay, this is not in scalar form. Doggone it. We need to find the perpendicular vector to this plane. Any ideas how I could find a perpendicular vector to this particular plane? This is how we have to solve this thing, because our formula involves the scalar form of the plane. How are we going to find a perpendicular vector to that? Gee, if only we had a tool, some way of finding perpendicular vectors. Any ideas, Maddie? No, this really puts people on the spot. I did it this morning. This is a direction vector that lies on the plane. This is a direction vector that lies on the plane. I can take the...
It's not the cross product, is it?
It is the cross product.
It is? Okay, I was like, wait, dot.
That's
dot.
right. Yeah,
We're good.
okay. Yeah, good for you. Aiden said dot product for the record, but he was probably thinking cross product when he said that. Okay, so D1 cross D2 is going to give us the normal vector to that plane, okay? And it's going to be uniquely directed. Okay, I am going to do this. 1, 2, 3, 1, 2, 3, and I'm probably going to get it wrong. 4, 5, 6, whose idea was this? This is going to give us big numbers, okay? This is my easiest way to remember how to do the, oh no, this isn't going to be that bad. Okay, so here's our normal vector down here. 2 times 6 minus 5 times 3. Hope I got that right. 3 times 4 is 12 minus 6 is, oh, look at that. That's not so bad. And 5 minus 8. There we go. Did that just happen? It really did, didn't it? -3, 6, and -3. Maddie, did I make a mistake?
I'm still writing it down. I'm working through it.
Okay, you're just processing it now. Okay. If I did it right, this is a normal vector, and it's just a scalar multiple of that. So this is going to be easier for us to work with. Okay. Just waiting for our panel of judges now to determine if I've actually calculated the cross product correctly.
Yeah, no, it's good.
Our panel of judges has approved it. Okay. There we go. This is going to be our A, B, and C. We just need to find our D now. Okay. So, -x plus 2y minus z plus d is equal to 0. Oh, darn it. There's that darn d again. It's got d right in the name. How am I going to calculate d? I need a point on the plane. Any ideas? Where did the 2y come from? Oh, this is the normal vector here, right? Yeah. So I'm just using -1, 2, 1 as my x, y, and z. How am I going to calculate d? I need a point that lies on this plane. Any ideas? Well, actually, our position vector, 0, 0, 0 in this case, lies on the plane. So I'm just going to substitute a 0 in, -0 plus 2 times 0 minus 0 plus d equals 0. So d is equal to 0. Who did that? Whose idea was that? That was a good idea, actually. I like the example because planes where d is equal to 0, they pass through the origin. And it's something that we don't spend much time on in the course, is saying, okay, if x is 0 and z is 0, then we have a y-intercept, and what is that? Okay, there we go. So this is our, we now know what A, B, C, and D are, and so we can put them into our equation for the distance. So I don't know. How do I say distance from plane to Q? I don't know. I'm going to go distance. Otherwise, okay, so ax1 plus by1 plus cz1 plus nothing, which is d, all over square root of a squared plus b squared plus c squared. Okay. Now I just have to substitute in my values. So the absolute value of -1. And, oh, we just came across a new problem. We have no point to find the distance to. Okay. I'm going to refer to my panel of judges. What point do we want to use here? Come on, Maddie. Not 0, 0, 0 either, because that's 0.
Let's go.
Small numbers.
0.5. No.
Tricky. 2, 3.
1.
1. 2, 3, 1. Excellent choice. Okay. So my x1 is 2. And, 2 times my y1, which is 3. And minus 1 times my z, which is 1. Oh, that is so easy. Plus 0, which I'm not going to write down. I'm not going to even dignify that. And this is over the square root of, a squared, which is -1 squared, plus b squared, which is 2 squared, plus c, which is -1 c squared, rather. Okay. -2 plus 6 is 4, minus 1 is 3. 3 over the square root of 1, 5, 6, square root of 6. And then, of course, I'm going to rationalize that. Of course I'm going to rationalize it. we would never want to do anything else. Oh, look at that. And then this, that's going to turn into that. So root 6 over 2 is the distance from this plane to that point. And that point is just feeling a little bit orphaned right now. Feels like we don't care for it. But that's not true. All right. So there was a combination of two things there. Finding the point, the distance from a plane to a point as well, changing the vector form into the scalar form of the line. Okay. Last problem. We are going to set it up, but I'm not going to do it because this is a really long lesson. And you guys can finish it. And that is, what is the distance between two skew lines? Okay, once again, it's algebra and vector. When we say distance, we mean the absolute shortest point of approach, and we mean the perpendicular distance. Now you'll notice that we have a tool. We can find the distance between a point and a plane. Okay, now yesterday we also found out how to take skew lines, and we found out how to make parallel planes to those skew lines. Okay. And I'm going to quit saying K because it's getting very irritating. I need two lines that I know are skew. So line
K is
one.
the new gonna.
What's that?
K is the new gonna.
Or A or something like that. I am going to stop saying K. I vow that. Okay. Line one. I just said K again. All right. Line one. I need a position vector. And I'm not going to go to you guys for it because it's just too unpredictable. So there's my position vector, and here is my, here's my direction vector, -1, 3, 2. Oh, I love those numbers. There's line one. Position vector plus the direction vector. Here comes line two, -2, 5. Wow, that was really brave. 2 plus t times 1, 1, 4. All right. These lines are not collinear or parallel or anything like that because the direction vectors are not scalar multiples of each other, so I'm fairly comfortable. Okay, these are hopefully skew. I'm almost sure they don't intersect. So they're doing this, right? And if you rotate them, oh, look, there's a space between them. They're not intersecting in 3 space. What I want to do is I want to find the distance from here to here. Okay, all right. Here's the strategy, everybody. We're going to make 2 planes. One plane contains line 1. The second plane contains line 2. And those planes are going to be parallel. So they're going to be separated by the same distance everywhere, which means they're going to be separated by the same distance that line 1 and line 2 are separated by. Okay, we just have to make these planes parallel. So here comes plane 1. I'm going to give it away. It has a position vector 1, 2, -2. And it has a direction vector s times -1, 3, 2. And all I really need is I need that second direction vector. And I'm going to use u as my parameter, not mu, but u as my parameter. Too much friction. Oh my goodness, what could I use as a second direction vector that would make this parallel to line 2? I know you know. You're not saying? I'm actually talking to Aiden. Yeah, there we go. Okay, plane 2. It's now parallel to line 2. Sorry, plane 1. I said plane 2, didn't I? Okay. Now we're going to make plane 2, and it's going to be parallel to this one. Oh, plus t times 1, 1, 4. Okay. And then plus w times -1, 3, 2. Okay. Planes are parallel. And they're in vector form. But they're parallel. So the distance between those 2 planes that contain both lines is the same as the distance between the 2 lines at the shortest point of approach. We have a formula, people. That formula tells us the distance from a plane to a point. All I really have to do is pick a point on either one of these planes. Who can tell me a point on plane 2? Pick a point, any point, easiest point to pick. On plane 2, I'm just going to, I'm going to pick the position vector's tip, right? Okay, there we go. I am going to find the scalar equation of plane 1. How am I going to do that? I know you know. And if you said in your mind to yourself quietly, cross product of the two direction vectors, you're right. Okay, so A, B, and C is equal to the cross product of these two direction vectors. So negative 1, 3, 2 cross 1, 1, 4. So that is going to give me a normal vector to that plane. That normal vector is going to tell me my A, B, and C. I'm going to use the position vector to calculate D. Then I'm going to plug it into my formula that tells me the distance from the plane, in this case plane 1, to this point that just happens to lie on plane 2. And that's going to be it.
Is it a -1 there in the first, on the first direction vector? Or did we...
Yes, it is. I made an invisible one just because I thought it looked better on the internet, but
That makes sense.
yeah,
Gotcha.
yeah. But I'll color it in. I'll color it in this time. I'll make it visible. All right. So that's it. So we've looked at the scalar equation of the plane. We know that A, B, and C are the normal vectors. We're given a point on that plane. We know how to find D. If I give you a normal and a point, you're able to find it. Okay. We looked at finding the formula for the distance from a point anywhere in space to a plane, and that's the shortest distance. We've also looked at changing vector form to scalar form by taking the cross product of the direction vectors and finding the normal vector, okay? I could give you 3 points that are just in 3 space. You should be able to figure out what a position vector is in 2 direction vectors given those 3 points, okay? We did not do an example like that because they're long and I make lots of mistakes when I'm doing the negatives. Last thing, we found the distance between two skew lines. That was that. And there we go.